Welcome to today's central exercise session. As usual, we'll be happy to take your questions on our chat channel. The chat is available at chat.tum.de. And please use this channel here, MA9711-CE, for your questions. The chat channel will, as usual, be moderated. And today's moderator is once again Alyssa Fernandez.
Hello, Happy New Year, everybody. Yeah, so as always, I will be reading the questions that they are coming from the chat, and whenever Michael gives me the chance to give them, to read them aloud, I will read them in the session.
Okay, wonderful. Thanks a lot. So also from me, Happy New Year to everyone. I hope you had some time to relax during your Christmas holidays. I hope you also had some time to maybe review the topics that you didn't understand so that you have brought lots of questions. We'll discuss sheet number 8 today, which is mainly about orthogonality and orthogonal projection. So questions on this sheet are welcome here in the central exercise session. For other questions, please refer to the questions and answer sessions, which have already restarted this Friday. Registration is online on Moodle for the next round currently. And also there's our tutorial sessions, our hands-on sessions, each Thursday from 2 to 5. The login data is on the Moodle course page. So if you have any questions on any sheet or any topic that you'd like to discuss, those would be the best place to do that. So let's start with problem sheet number 8. Let me start the screen sharing once again. So sheet number 8, as I said, is mainly about orthogonality and orthogonal projection. And we'll just start with exercise C81 as kind of a warm-up problem. So here we have 4 vectors containing 2 real parameters. Let me just write those down. So the vectors are 2, alpha minus 2, that's x. Then we have a vector called y, that is 3, 1, beta. And alpha and beta are the real parameters. And 2 more, u is 4, 3, alpha. And v is beta 4 minus 5. Parameters alpha, beta are some real numbers. And the task is to compute values for alpha and beta such that the scalar product of x and y is 0, and so is the scalar product of u and v. So x and y need to be orthogonal, and u and v also need to be orthogonal. Scalar product of 0 simply means x, y are orthogonal, and also u and v are orthogonal. Okay, so let's do that. We just compute the scalar products to see what the outcome is here. The scalar product of x and y is simply given as, it's a standard scalar product, so it's simply given as x transpose y. So what we have here is x transposed is 2, alpha minus 2, and y is 3, 1, and beta. So basically, we just multiply each component of y with the corresponding component of x. So these two and these two, and then sum up the result. And what we get is 2 times 3 plus alpha times 1 plus minus 2 times beta. So that would be, let's see, 6 plus alpha minus 2 beta. And of course, that is going to be 0 if and only if alpha minus 2 beta is equal to minus 6. And then we can do the same thing for u and v. So the scalar product of u and v, I'll look up there, u and v are given here. So again, that is U transpose V, and that is 4, 3, alpha, and V is beta 4 minus 5. So we get 4 beta plus 3 times 4 plus alpha times minus 5. So altogether, this would be, let's see, minus 5 alpha plus 4 beta plus 12. And then this is 0 if and only if minus 5 alpha plus 4 beta equals minus 12. So what we have here, and here, are simply two linear equations in the variables alpha and beta. So just solve this system of linear equations here. And we do this as usual using Gaussian elimination. The first one, alpha minus 2 beta equals minus 6, looks like this in tableau form. And the second one, minus 5 alpha plus 4 beta equals minus 12. That would look like this here. And to solve that, we simply add 5 times the first row to the second one. So we get 1 minus 2 minus 6. We just copy the first row. And for the second row, we get, let's see, 0. And then we have 4 minus 10. That would be minus 6. And minus 12 minus 30, that's minus 42. And then we can solve this through backward substitution. So we have beta equals minus 42 over minus 6. That would be 7 plus 7. And then alpha is minus 6 plus 2 beta. So it's minus 6 plus 14. And that is plus 8. So the parameters that we determined are uniquely determined, and the right values are alpha equals 8, beta equals 7. Okay, let's see if you already have any questions on this one.
Yeah, there are a couple of questions related to the exclamation mark that you have written on top of the quality sign.
This one here?
Yeah, like there was a question saying, like, is it really a mistake not to put the exclamation over the quality sign, and why did you do it?
No, that's totally fine. You don't have to write this exclamation mark. I'm just doing that to signify that this is not exactly a reformulation of this left-hand side, but it is a requirement that's coming from the problem statement. And to signify that, I put this exclamation mark here. You don't have to do that. As long as it's clear what you're doing, not necessary.
Then there is another question that it says, like, can you also solve it differently without Gauss elimination? Yeah.
In the end, what you have to do is you have to solve the equation system consisting of these two equations here. It's up to you how you want to do that. You don't have to use Gaussian elimination for that. I do recommend that, however, just for practice, because you will need to master Gaussian elimination, and I don't see a good reason not to use that here.
Yeah, so substitution would be also a possibility, but out of practice, it is recommended to use it.
Yeah. Yeah. Of course, any other method is fine as well, as long as you somehow document what you're doing. You shouldn't just put the values out of thin air, at least not without proving that they are actually correct. Yeah, but otherwise, as long as it's clear what you're doing and, of course, correct, then that's fine. You don't have to use Gaussian elimination, but that is my recommendation, purely for practicing.
No more questions.
Good. So then let's move on to something a little more challenging, maybe. Problem CH2. So here we have 2 points, P and Q. I'll write down the coordinates. P is given as the point 3 minus 2. Q is given as the point 6 minus 3. And we also have a linear subspace G. G is simply the span of 1, 1. So that's the line with direction 1, 1. The bisector of the positive quadrant, as the problem statement says. And the task is to determine the length of the orthogonal projection of the line segment PQ onto that line G. And to clarify what we are going to do here, let's start with a quick sketch of the situation. So let's see if I get that right. So we want about, start here. Say this is -4, -3, -2, -1, 0, 1, 2, 3. That should be sufficient. And then here we have the x1 axis. So that's the x1 axis. This is going to be the x2 axis. And we need that up to 6. So 1, 2, 3, 4, 5, 6. Maybe one more. And let's sketch those 2 points. So P is at 3, -2. So that is here. That's the point P. Q is at 6 -3. So that is here. So this here is the point Q. And then the question is basically about the line segment. So we have to connect P and Q. So that's this line segment PQ. And the problem statement is asking for the projection onto the line spanned by this vector 1, 1. So 1, 1, this vector is here. And that means the line spanned by this vector, that would be this line here. So that is the linear subspace G. And geometrically, what we're doing is we're taking orthogonal projections of P and Q onto that line. And that means like we're connecting, or we are decomposing, that's the word I was looking for. We're decomposing the vector P into a part that is orthogonal to the line and a part that is parallel to the line. So if this here, let's see if I can sketch that. If this here is the vector P, so the vector that points to this point P here in our system, we want to decompose that into a part that is orthogonal and a part that is on G. And we can do this by simply drawing this triangle here on this one, where this line here is orthogonal to G. And then the part that is parallel to G is this one. So you can write this vector as this blue part plus this red part here. And the blue part is the projection of P that we're interested in. So this here is, let's see if I can write that, projection. Oops, sorry. Projection on G of P. So this is that part here. And the corresponding point is, of course, this one here. So let's call that point P prime. And we can do the same thing for Q. And again, what would roughly mean, we need this line here, again, orthogonal to G. And then the decomposition would look like this. So this is the orthogonal part. And this here is the part parallel to G. So that would be the projection onto G of the point Q. And we call that Q prime. So this here is the point Q prime. And of course, once we have those 2 points, the length of the line segment can easily be computed. So basically what we have to do is we have to find those 2 points, P prime and Q prime. So find P prime, that's going to be the orthogonal projection onto G of the point P. And Q prime is going to be the orthogonal projection onto G of the point Q. And what we have to do to compute an orthogonal projection, basically what we need first is an orthonormal basis of the space that we're projecting onto. So the first step here would be to determine an orthonormal basis of that space G. So determine an ONB of G. Well, that's easy. G is spanned by just the vector 1, 1. So we don't have to orthogonalize anything. It's just one vector. Only thing we have to do is we have to normalize that. And of course, the span of the vector 1, 1 is the same as the span of any normalized version. And the norm of that vector is square root of 2. So we just divide by square root of 2 to normalize that vector. And we'll call this vector here. So this here, that will be our vector n for normal vector. And then the only thing left to do is to do the projections, is basically to apply the formula that we learned. So the projection onto G of the point P is then simply given as the scalar product of the vector with this normal vector times the normal vector. And if we have more than one basis vector, then we would add the other components in the same way. So we would take the scalar product of P with the next basis vector times that basis vector plus the next one and so on. Yeah. So in this case, we only have one basis vector. That makes it a little easier. But what is that? The point P is, what was that? 3 minus 2. Yeah, right. 3 minus 2. The point N is 1 over the square root of 2 times 1, 1. And here again, we need N, 1 over the square root of 2 times 1, 1. And as you can see, we can easily take this factor here out of the scalar product. And we can also move around this factor here. So if you put those both in front of the scalar product, then we would get 1 over the square root of 2 times 1 over the square root of 2 times the scalar product, now without that factor, times the vector, again without the factor. So what we have is this 1 over square root of 2 squared is the same thing as 1 over 2. This scalar product here, that would be 3 minus 2. And then we still have that vector 1, 1. So, well, 3 minus 2 is just 1. So what we get is 1 over 2 times the vector 1, 1. So that's going to be our point P prime. And as can easily be seen, this is actually on the line G. So you should verify this. If you project something onto a linear subspace, then of course the result should be inside of that linear subspace. And that's something that is easily checked for a line in R2. The result must be a multiple of the original vector of this 1, 1 direction. Okay, so that's the first point. And the second one is computed in the same way. So we just take the scalar product of Q and N now and multiply that by N. And Q was, what was it? 6 minus 4 or something like that. 6 minus 3. 6 minus 3. And then again, we have 1 over 2 times 1, 1 times 1 over square root of 2 times 1, 1. And this is 1/2. So again, I take these two 1 over square root of 2 factors outside and combine them. So that's 1 over 2. times the scalar product of 6 minus 3 with 1, 1. That is then 6 minus 3 times the vector 1, 1. So now we get 3 over 2 times 1, 1, and that's q prime. So this is the projection of the points P and Q onto that line. And of course, now we can easily compute the length of that projection by just taking the difference of those two vectors and then computing the norm. So the difference is, let's see, 1 over 2, 1, 1 minus 3 over 2, 1, 1. So that's the same thing as 1 over 2 times 1 minus 3 and 1 minus 3. And that means what we get is the norm of 1 over 2 times minus 2 minus 2. So that's the norm of minus 1 minus 1. And that is the square root of 1 plus 1. So both entries squared and then taking their sum. So the distance that we're looking for is the square root of 2. So this is the final result here. So let's see what questions you have on this one.
Okay, so there are some questions here. So starting from the first question, it was asked is that with this approach, we first compute the projections of the 2 points and then calculate the distance between them. Can we also first compute the line PQ and then project that line on G and then calculate its length?
Of course, you could also do that. Yeah, you could also compute the line connecting those two and then project that and compute the length of that projection. That's fine.
How do we calculate n?
So this vector n, what you need is basically you need an ONB of the space that you're projecting onto. And the space that we're projecting onto, this G, is defined as the span of 1, 1. So we need an ONB for that span of 1, 1. And for that purpose, we just turn this here, this 1, 1, into an orthonormal basis. And the only thing we have to do here is normalize. There's no other basis vectors, so no need to care for any orthogonalization. If you have more vectors, then what you would do is you would apply Gram-Schmidt's method. We're going to do that in the next problem.
Okay, then there is a question that it says, can you please explain how did you got 1 over root of 2? Well, this is computing the norm.
1 over what was that? 1 over 2?
The square root of 2, because this is the norm of the vector 1, 1. It's 1 square plus 1 square root.
Yeah, so what I'm doing here is I'm computing the norm of the vector 1, 1. And that is defined as the square root of the sum of the squares of the entries. So the entries are 1, 1. That means we have 1 squared, and the next entry is also 1 plus 1 squared. And then we're taking the square root of those, and that's square root of 2. So that's the length of this vector 1, 1. And to normalize, we just divide by that length. So the resulting vector, this n, then has a length of exactly 1. And that's what normalization means.
Yeah, there is another question. It says, can we also solve this by determining the angle between PQ and 1, 1 and then calculating the distance with the cos rule?
Between PQ and 1, 1 and what rule?
I think he means like the cosine formula for the angle.
It should be possible, but it doesn't seem easier than this one. So basically, you would have to compute almost the same things that I did, plus a little more. I guess. I haven't tried that approach, to be honest.
Okay, then there is another question. It says, is there a difference between the first notation P prime and the second one equal to Q? I have to say I don't get that one.
Yeah, me neither. What exactly was it? The first notation P prime and the second one?
Q.
Q. Well, Q is a point and P prime is a different point. But I probably don't get the question right. So maybe you would like to rephrase that.
Yeah. Do you need to move 1 over a square root of 2 to the front of the scalar product, or can you move it where you want it?
So this one here. So you can take that, as I said, you can take that outside of the scalar product. Whether you move it here or here doesn't really matter. It's a real number, so you can move it any way you want. Yeah, whatever suits you best. I usually try to move all the factors, this one in front of the scalar product, but you don't have to do it this way. You can also just keep it here if you prefer that. That's fine. I'm just doing that because I have the same factor twice. So if there's a square root in that factor, then moving them both to one place and multiplying usually gets rid of the square root. But again, you don't have to do that. I just find it convenient to do so. Sorry.
No, yeah, I'm sorry. Why don't we compute q prime minus p prime to get the length of the orthogonal projection of the segment PQ?
So you mean, why don't we compute instead of this expression here, you would want to compute the norm of q prime minus p prime. Is that right?
Yeah, I guess this is, yeah.
Yeah, it's the same thing. So what you could do is q prime minus p prime is the same as minus p prime minus q prime, like this here. And as you know, for a norm, the sign doesn't really matter. So this norm is the same as the norm of p prime minus q prime. So it doesn't matter which one you use.
Can you please explain how you solve the 1 over 2 1 t minus 3 over 2 times 1 I don't really get that one. I'm sorry. Yeah, okay, that one. Maybe the projection, right? To get
which one?
Like to get to p prime.
P prime. So this step here.
Yeah, I guess this is, yeah.
So basically what I'm doing, I want to solve this. I want to compute this expression here. That's the projection, right? So I'm multiplying this by n, and the scalar product of p and n basically tells me how long is the part of p that is parallel to n. And the important thing for that is to have n normalized. That's why I normalized it before. Yeah. So you need a normalized version here, or in general, an orthonormal basis of the space that you're projecting onto. Yeah, but once you have that, that's the formula. And then I just substitute the values here. So I have 3 minus 2 for p. This is my n, and this is again my n. And then remember, by bilinearity of the scalar product, I can just move out any real numbers. And I'm moving out this here to this place here. And again, this is a real number, 1 over square root of 2. I can move that anywhere in this computation. And I'm choosing to move it here, because if I multiply those two, then I get 1 over 2. So that gets rid of the square roots. And the rest is, I just have to compute this scalar product. And that means I take, that means I take 3 times 1, that's the 3 here, and minus 2 times 1, that's the minus 2. 3 minus 2 is 1, so I'm left with 1 over 2 times 1 times 1, 1. And that's p prime. I hope that is the explanation that you were looking for. If there's a specific step you don't get, then please just ask again.
Yeah. Can you please go over the computation of the length between the 2 points?
Yeah, sure. So what you do here is I want to compute the length, so the norm of this difference. And what I do is I just substitute the points. This is p prime. This is q prime. And then I'm factoring out 1 over 2. So this is 1 over 2 times, let's maybe insert that step here in the middle. This is the same thing as 1 over 2 times 1, 1 minus 3, 3. Right? This is this factor 3 here. I take this inside the vector, and I factor out the minus 1 over 2. So this is where I end up with, oh, sorry, forgot to close the norm here. So this is what I end up with, and 1 minus 3 is minus 2. So I get this. And then again, I just take this factor into the vector, that yields -1, -1. And then I compute the norm of that. So the norm is square root of -1 squared plus -1 squared, and -1 squared is +1. So it's +1 + 1, and that's square root of 2.
How could we solve that if there were multiple vectors in the span of G?
If there are multiple vectors in the span, so what you would do in that case, let's say you have, I'm calling it U instead of G to avoid confusion. Let's say we have U, any vector space, and we have a basis for that one. So let's say this is given as the span of V1, V2, V3, just as an example. Let's make it 3. Then the first thing we do is, again, we would compute an orthonormal base of U. And let's say that orthonormal base is B1, B2, B3. So we have 3 vectors that are pairwise orthogonal to each other and all have length 1. And then to compute the projection of a vector x onto U, what you would do is you would determine the scalar products of x with the basis vectors, so normalized, orthonormalized basis vectors, so B1. This is the part of x that points in B1 direction. And then you would just add the other components. So the idea is basically to decompose x into components parallel to B1, B2, B3, and a third component that would be orthogonal to each of those. And the projection is only the components in directions that are contained in the vector space U. So this is the projection, and the orthogonal part is the rest, so to say. So that's what you would do if you had a vector space with not just one vector in the basis. So of course you'd have to determine this O and B first, and that is usually done by Gram-Schmidt's method. Again, we'll see about that in the next problem.
Okay, then can you please show graphically where exactly the projection PQ is?
So the projection of PQ here in that sketch, that would be, let's see, one more color here. So this here is P prime, this here is Q prime. So the projection, that would be this. And of course, if you compute that vector that connects P and Q, then graphically that vector would normally be attached at the origin. So the projection would also be attached at the origin, but the length would not change. Yeah, so if you really want to have the projection of this exact line segment, that would be it.
Okay, now why determining the distance between P prime and Q prime?
Well, yeah, we are determining that because it asks for that in the problem statement. Or is there more to the question?
Yeah, I mean, like, yeah, maybe this one we cannot really, because I would have to read the formula and I don't know how, like if you have the norm of 1/2, 1, 1 minus 3 half 1, 1. So writing P prime and Q prime, right?
So like this here?
Yeah, correct. Then it's 1/2, 1 minus 3, 1 minus 3. Yes, the norm.
Yeah.
Why is 1/2 minus 3 half 1/2?
It's not. It's no. 1 minus 1. That's exactly what I get here. Minus 1, right? So it's 1/2 minus 3/2. That's minus 1.
Okay, I guess.
So this maybe this is not clearly readable. That should be a 2 actually, or a minus 2.
Okay, yeah. If it is not clear, maybe like insist. I'm not sure whether. Okay, and how would we compute the projection if the basis? Okay, well, this was already answered. Okay, could you please show how we compute PQ first and then project it onto G?
Well, you just take the difference and you have one vector, you compute the projection of that one. I guess that's something that you should be able to do yourself, hopefully. Maybe it's a nice practice. Try to do this yourself.
Yeah, okay. So then it's also, the next question would be related to that, so try it yourself. I did not know that we have to perform 3 different steps. I just computed the projection on G and defined V as the vector Q minus V, and I got the same result. Is this also right?
So you projected the difference vector P minus Q directly onto G.
Q minus V.
Q minus, what is V?
Yeah,
Q minus P or?
Well, maybe just try to write it better.
Yeah, so once again, if you compute this difference vector here and then compute the projection of that one directly onto G, that's also fine. Should give you the same result lengthwise. You're just not getting the projections of the individual points, P and Q, but that's nothing the problem statement asks for that. So that solution would be fine, of course.
Now it says another one. So you split it up into a projection and a line which is orthogonal to G.
Yeah, basically that's the idea of the projection. Yes. So you have a vector, you want to split it up into a part of that vector that lies in the space that you're projecting onto. So in this case, that lies on G, and a part that is orthogonal to G. For example, if you take this vector here, this P, that's the vector P, right? What the projection does is it splits up that vector P in a part of that is parallel to G, so it lies in G, and a part that is orthogonal to G, this part here. And the projection gives you the part that is inside our G, or parallel to G if it's a line. And then what is left, so the difference, this vector minus this vector, would give you the orthogonal part here. So basically we're decomposing that into a part that is in that subspace G and a part that is in the orthogonal space to G.
And the last one is, could we just ignore the O and B's and solve by finding P prime and Q prime through the scalar products of a vector with a scalar product of 0 with G?
A scalar product of 0, so probably yes, if you do it correctly. I recommend against doing that, however, because that usually gets messy quickly. I wouldn't try it that way. I'm not quite convinced that you would get it right, but in theory, that is possible.
When do we use the formula projection U V A times the transpose of A V?
You use that when you have a meaningful A given.
Okay, so, and one more question.
Yeah, that appeared, for example, in the context of the least squares method. And there you have this A that kind of describes the vector space that you're projecting onto. So the question is, what is the description of the vector space that I have? And if that is somehow described through that system of linear equations, or the solution space of that system of linear equations, that is implicitly described through the matrix A, that's when you use that method. Otherwise, the easiest is usually to use this projection formula here, or this more general projection formula down here. But of course, you need to have an O and B first to be able to do that. And implicitly, all of these are doing the same thing, of course. Okay, let's go for the last one, C83 then. And after that, I'll have a few words on the exam to say, so please stay tuned, don't leave. But I'd first like to finish with this sheet here. So as I said, we're going to an example. We're going to get an example for Gram-Schmidt's method now. And here we have an example that is in R4 to make it a little more interesting. So U is given as the span of two vectors, v1 and v2. And those are 2, 1, 1, 0. And v2 is 4, 0, minus 2, 2. And the problem statement asks for an O and B of U and also of the orthogonal space. So that's what we have to determine. And we'll start with the O and B of U. To determine an orthonormal basis of any vector space, what you do is you start with any basis and then you apply Gram-Schmidt's method. So that's what we're going to do here. We're going to apply Gram-Schmidt's method to the basis, given by v1 and v2. So, and the steps that you do are basically the same as we just did in the projection before, just a little twist. So what we do is we start with the first basis vector. And which one is the first? That's arbitrary, that's up to you. So here we'll start with v1 just. And we'll define the first basis vector of our O and B. I'm calling those b1 and b2. So the first basis vector of our O and B is going to be the vector v1, and we're going to normalize it. So we're going to divide v1 by its norm. And that means we have to compute the norm of v1. Now v1 is 2, 1, 1, 0. So the norm is the square root of 4 plus 1 plus 1 plus 0. And what we get here is the square root of 6. So we have 1 over the square root of 6 times 2, 1, 1, 0. So that's the first vector of our orthonormal basis, b1. Now for the second vector, what we do is we take v2, the next vector in our standard basis here, and we decompose that. We decompose v2 into a part that is parallel to b1, or in general, lies in the span of the basis vectors that we already have, and a part orthogonal to that. And we only keep the part orthogonal to the original, to the space we already have. Yeah, we don't need the parallel part because that's already been taken care for by b1. We just keep the part that we need on top of that, what we already have. So I call that b2 prime because the result is going to be normalized afterwards. And it's going to be b2 then. So b2 prime is an intermediate step. And we get that by taking v2, so the original vector, and then we subtract the projection of v2 onto the space spanned by b1. And that is this part here. So this here, that is the projection onto the span of b1 of v2. So that's the part that lies in the space that is already being taken care of by b1. Right? And what we keep is the rest, v2 minus that part. So that's the part that is orthogonal to b1. And that's what we want for our orthonormal basis. So we just have to do the computations here. Let's see, the points that we have are v2 was 4, 0, minus 2, 2. And then we're subtracting 4, 0, minus 2, 2. Scalar product with 1 over the square root of 6 times 2, 1, 1, 0 times 1 over the square root of 6 times 2, 1, 1, 0. So that is 4, 0, minus 2, 2. Minus, again, I'm taking out this 1 over square root of 6 here, and together that yields 1 over 6. So I'm left with the scalar product. I'll write it down one more time. 4, 0, minus 2, 2, with 2, 1, 1, 0, times 2, 1, 1, 0. And what I get is the scalar product is, let's see. So what we have is 4 times 2, this is 8, plus 0, minus 2, this is 6, plus 0, so that should be 6, right? Times 2, 1, 1, 0. So 6 over 6 is 1, and that means we just have this vector minus this vector. So what we get is 2 minus 1 minus 3 and 2. That's 3 here. So this is B2 prime. Just for a quick check, you don't have to do this, or you don't have to write this down, of course, but you might want to do this quickly in your head to be sure that you didn't make a mistake here. The result should now be orthogonal to B1. So let's give that a quick check. If we compute the scalar product of these two, then we would expect that to be 0. And that scalar product is 4 minus 1 minus 3, and that is indeed 0. So the result seems to be correct. And now we have the orthogonal part, so to say. The only thing that is left for an orthonormal base is to normalize that. And that is going to be our B2. So that's B2 prime divided by the norm of B2 prime. And the norm of B2 prime is, let's see. So this here is B2 prime. That means what we get is square root of 4 plus 1 plus 9 plus 4. So that is 18. Well, not the most beautiful result, but we can live with that. Square root of 18 times 2 minus 1 minus 3, 2. So that's B2. And there's our orthonormal basis for U. And again, that orthonormal basis is B1 and B2. B1 is 1 over the square root of 6 times 2, 1, 1, 0. B2 is 1 over the square root of 18 times 2 minus 1 minus 3, 2. So this is an ONB of U. And this is, of course, not the only possible ONB of U. And the result heavily depends on how you start. If you start with V2 as your first vector, which you can do, then, of course, the result will be different. Or might be different. In this case, it will be different. Okay, before we go over U-ortho, are there any questions already?
Yes, they are. So the first question is, a question about how the task is formulated. Is there a difference between determining an orthonormal basis for the span and an orthonormal basis V for the span?
Well, in the second case, the basis gets a name, so that's it. And I would usually do that if I reuse that basis in the problem statement later on, so it might be convenient to have a name for that. Otherwise, no difference.
Is it possible to first calculate an orthogonal basis and then normalize the vectors to get an orthonormal basis?
If you manage to do that, you could do that, but you won't. So the problem here is, at least if you're using Graham-Schmidt's method, then you have to compute these projections here using the vectors that you've already computed. So here's B1, and you need to have an orthonormal basis of the space that you have already covered. So in this case, you need a normalized version of B1. Yeah, B1 wouldn't do. That would not give you the right projection. That's why you need an ONB of all the vectors up to the very last one. So in theory, you could do without normalizing the last one and then normalize later, but that's actually the same thing. If you manage to come up with an orthogonal basis by some other way, not using projections like this, then of course you could do that. But if you're using Gram-Schmidts, you have to normalize in every step. Otherwise, these projections will be wrong.
And can you write down the formula if there are 3 vectors in the span?
We'll continue in just a minute when we do this U-ortho, so we'll have that automatically. Then
there was a question. I'm sorry, Jonas. I still don't really understand. I'm gonna read it, but would it be possible to show the computations after that in a sketch? And then I kind of like ask which computations and what we compute right now. I'm not sure really. I'm really following.
Not really sure what you mean here, especially seeing as we're talking about a 4-dimensional space, and I don't see how you would want to sketch that in a way that is comprehensible to our 3-dimensional correctors. So that's not something you want to do, believe me.
Could you maybe shortly explain once again what B2 prime represents?
So what we do here is, let's see. So we have this B1. I'll start with that. So this is, let's say we have V1 here, and then we normalize that and we get B1. So let's say this here is B1. B1, this is V1. So basically the same vector, but with length 1 now. And then we have this other vector, V2. And let's say that looks like this. So let's say this is V2. Then what we do is we decompose that V2 into a part that is parallel to B1 and a part that is orthogonal to B1. And doing that means what we have to do geometrically. And of course, this is only a 2D sketch now, so that won't take us that far. We have to use this line here. And you can see this is basically the decomposition, right? So this V2 can be written as the sum of this vector and this vector. And the first one, I think I put that in blue. That first one here, this part here, that would be the projection of V2 onto the span of B1. Right, so this is what we compute when we compute the scalar product of V2 and B1 and multiply by B1. And then this red vector here, this one, that would then be the vector that we compute. So this is, this is V2 minus the projection. Right, so again, that's the blue part here. That's the blue part, this one here. And if we just take V2, subtract that blue part, then that red part is what remains. And that is exactly what we take as our B2 prime. And then for B2, we just normalize that. That's the idea here. So we decompose the original vector V2 into a part that is already covered by B1, so to say. So we don't have to include that part into the basis. And the additional part that is then orthogonal to B1. And we need to keep that part so we can kind of reconstruct this V2 so that the vector space stays the same in the end. But now with two vectors that are orthogonal to each other.
No more questions.
Okay, great. So then let's go on with the orthogonal space to U. So now we compute a basis for U ortho. And we do this in the following way. We start with the basis of the whole space, R4, that includes the vectors for U that we have already found. So we take this basis, these O and B for U that we have already found, and we extend that to be a basis of R4. And then we just orthonormalize that once again. The first two vectors are already orthonormalized, so nothing to do there. But we add a third and a fourth vector, and that will give us an orthonormal basis of R4. The first part of that is our basis of U. So the second part is necessarily the orthonormal basis of U ortho. So what we do is we take some basis of R4 that includes the vectors B1 and B2 that we have found. So we extend that basis of U to a basis of R4. And then we apply Schmidt. What we get then is an ONB of R4 of the form where we still have B1 and B2 in there, because that will be the vectors that we'll start with in our orthonormalization, so those don't change. And then we extend that by two more vectors, B3 and B4. R4 is four-dimensional, so we need two additional vectors. This is the basis of U that we already have. And these other two, those will then be a basis of U ortho. And that's what we're looking for. So the first step is to extend the basis. And that's more or less arbitrary. You can take whatever works here. So we're starting with B1, B2. And I'll just try to extend that by U1, U1 and U2, where U1 and U2 are the unit vectors. So what I mean is this vector here, that's U1, and this vector here, that's U2. And of course, I'm not sure yet whether this is actually a basis. I just extended this by two more or less arbitrary vectors. I don't really know if those four are actually linearly independent. But let me just start with this, and in case it turns out not to be enough, I can always add more. So what you could do, just as a side note, if you wanted to be sure, you could also, instead of a basis, get a generating system. So you could just add U1, U2, and then also U3 and U4. And now we can be sure that the span of this is actually R4. So those are enough vectors. They're not linearly independent, though. But what will happen in the Gram-Schmidt method is that will automatically detect if you have linearly independent vectors. But let me first demonstrate how the method works with more vectors than just this one, and then I'll discuss why this will happen and what will happen if we have linearly dependent vectors. So we start by extending the basis. Then step 2, what we do is we orthonormalize the spaces. Orthonormalize, starting with B1, B2. So the only thing you don't want to do is you don't want to change the order. So the basis you already have should always be the first vectors of the resulting O and B, because those are already orthogonal and normalized. So no work to do here, right? So that means we start by computing the third basis vector, B3. And as before, we start with B3 prime and then normalize. And B3 prime, this is the vector that we get from this first extension here, 1, 0, 0, 0. So we again want to compute the part of this vector that is orthogonal to now the span of these two, to U. Okay, so what we do is we take this vector and then we subtract the part that is parallel to B1, and that part is 1, 0, 0, 0. times b1 times b1. And then, next step, we subtract the product of this vector that is parallel to b2 in the same way. So we take the scalar product of 1, 0, 0, 0 with b2 times b2. And that here, this expression, basically means we are subtracting the projection onto the span of b1 and b2 of 1, 0, 0, 0. So what remains is, again, the difference between the actual vector, 1, 0, 0, 0, and its projection onto the space that we have already covered by b1 and b2. So this remainder is necessarily orthogonal to b1 and b2, to the whole space spanned by b1 and b2. Okay, so let's do the computations. So remember b1 and b2, we have those somewhere here, right? That was b1, that was b2. Again, I'll take out that factor in front of b1 and b2 right away. So what we get is 1, 0, 0, 0 minus the factor in front of b1 was 1 over the square root of 6. So I have that once here and once here. So I get 1 over 6 times. Now there's the scalar product of this vector and this vector here. That's simply 2, right? So this times 2 times, and now the vector b1, 2, 1, 1, 0 without normalization because I have that here already. And I can do the same thing for b2. b2 was 1 over the square root of 18. So if I'm taking out that factor, I get 1 over 18. Again, I have that 2 times, once in the scalar product here and once here. Then I have the scalar product of this vector and b2. So that simply yields the first component of b2, which is 2 times, and b2 without normalization is 2 minus 1 minus 3 and 2. So that's what we get here. And let's see, what does that mean for the result? We have 9th, so let's bring that 2 to 9th each. So this is 1 over 9 times 9, 0, 0, 0, minus 2 over 6 is 1 over 3 is 3 over 9. So that's 3 over 9. And 2 over 18, this is 1 over 9. 2 minus 1 minus 3, 2. And now I should be able to get the result. So that is 1 over 9 times, let's see, we have 9 minus 6, that would be 3, minus 2, that would be 1. Then we have 0 minus 3 plus 1, that's minus 2. 0 minus 3 plus 3, that's 0. And finally 0, 0. And here we have minus 2. That is minus 2. Great. Okay, so that is B3 prime. And to get B3, what I'm doing is I'm taking B3 prime and I'm dividing it by the norm of B3 prime. And of course, as the result will have a length of 1 anyway, it doesn't really matter whether I take this vector here and normalize that, or whether I first scale it and then normalize the result, right? So if I have a vector like this, I normalize that, I would get this here. So that's the same vector with length 1. If I scale that first, for example, multiplying it by 2, I will get that, and then normalize this red vector. Again, the direction is the same. I just scale it down to length 1. I will get the same vector here. So what I can do here is I can multiply this by 9 and effectively forget about this fraction here. And then just normalize this part. Result will be the same. And that's what I usually do. Of course, you can also use this 1 over 9 and take that into the norm. And what will happen, it will cancel out. Yeah, so that's up to you. But let's see what happens. So we have a square root of, now this is 1, minus 2 squared is 4, 0 squared is 0, and minus 2 squared is 4. And then we have this vector here. So what we get is 1 over the square root of 9, that is 1/3. 1 minus 2, 0, minus 2. So that's our third vector in the basis of R4. Again, you can give that a quick check to see if that vector is actually orthogonal to B2 and to B1. And you actually should do that, at least in the exam. Give it a quick check, see if that's correct before you use the result for computing the next vector. And if you do that, you will find out, hopefully, that I have made no mistake here. So that's the third vector. And of course, number 4, that works in the very same way. So now for B4 prime, that is based on this vector here now, 0, 1, 0, 0. So we'll start with that. And we'll subtract the projection of that vector onto the space spanned by B1, B2, and B3, so that we only retain the orthogonal part. So that means we have to subtract the vector, the scalar product of 0, 1, 0, 0 with B1 times B1. We have to subtract the scalar product of that vector times B2 times B2. And we have to subtract the scalar product of that vector with B3 times B3. And again, that here means we are subtracting the projection onto the span of B1, B2, B3 of 0, 1, 0, 0. And what remains is the part that is orthogonal to that space, to that span here. Now let's do the computations. We get 0, 1, 0, 0. Minus B1 was 1 over the square root of 6 something. So if we take out that factor twice, we get 1 over 6. The scalar product of this vector here with anything means we just take the second component. Remember, B1 was, what was that? 2, 1, 1, 0. So the second component is a 1. So that's our scalar product. Minus B2. B2 was 1 over the square root of 18 something. So if we take out that factor twice, we get 1 over 18 times B2 was 2 minus 1 minus 3, 2. So the second entry is a minus 1. So that's going to be our scalar product here. And finally, we have B3. B3 had a factor of 1 over 3. So please be careful with that. 1 over 3 squared is 1 over 9. Please don't make the mistake of writing 1 over 3 here. If you take out both factors. Times B3 was a vector, let's see, 1 minus 2, 0, minus 2. So the second entry here is a minus 2. And that's exactly the scalar product that we want to compute here. So let's see. We get something with 18s, I'm guessing. So least common denominator is 18. That means we have 1 over 18, 0, 18, 0, 0 here. Then here we have minus 1 over 6 is 3 over 18. So that's 2110. Here we have minus 1 over 18 times minus 1, so that's plus 1 over 18 times 2 minus 1 minus 3, 2. And finally, doing it here, minus 2, so that's plus 2 over 9 or 4 over 18 times 1 minus 2, 0, minus 2. And let's see what we get there. This is 1 over 18 times. So the first component is here's 0. Here we get a minus 6. Plus 2 is minus 4. Plus 4 is 0. Then here we have 18 minus 3. That's 15 minus 1. That's 14 minus 8. That should be 6. Then we have 0 again here. Minus 3. Minus 3 is minus 6 plus 0, so that's minus 6. And finally, 0, 0, 2. And there is a minus 8, so 2 minus 8 is minus 6. Okay, so that is the same thing. We can factor out a 6 here, and we get 1 over 3, 0, 1, minus 1, minus 1. And again, we have to normalize that. So B4 is B4 prime over the norm of B4 prime. And again, I can just normalize this vector here instead of this one to get the same result. And that would be 1 over the square root of 1 plus 1 plus 1 times 0, 1, minus 1, minus 1. So what I get is 1 over the square root of 3 times 0, 1, minus 1, minus 1. So finally, I have my basis of U ortho. And that is B3 and B4. Well, let's write this down one more time. B3 was 1 over 3 times 1 minus 2, 0, minus 2. And B4 was 1 over the square root of 3, 0, 1, minus 1, minus 1. And again, a quick check whether the result is actually orthogonal to the other vectors doesn't hurt. And you should absolutely do that in an exam situation. Okay, so this is the orthonormal base of U ortho. So this is not just a basis, it's even an orthonormal base of U ortho. Okay, that completes this problem. So let's see what questions you have.
Yeah, but I'm going to start by a question myself, like the statement of the exercise says just the basis of U orthogonal.
Yeah.
So it wouldn't be necessary to normalize.
It would not be necessary to normalize, strictly speaking. However, for the computation of B4 prime, yeah, so once again, for this step here to work, we need an orthonormal basis for the space that we have before. So B1, B2, B3, those need to be orthonormal and also normalized. What you wouldn't have to do is normalize B4. That's the last vector. You won't use that for anything anymore. So you could stop. You could stop right here and just use this one. That would be fine. Or you could just do away with these factors if you prefer to write it down without them.
Okay, so there are several questions. Let's start. Could you also compute two vectors that are orthogonal to the vectors in U? I got the same vectors you found.
If you can find another method of doing that, then of course, yes, you can do that. The question is, how do you get vectors that are orthogonal to those in U, to both, and then also to each other, or at least linearly independent? I mean, if you're just looking for an orthogonal basis, then they still have to be orthogonal to each other as well. And usually the easiest method that I know of is Gram-Schmidt's orthonormalization method. But if you can do that in a different way, then that's fine.
Why do we need 2 additional vectors in 8.3? Is this the task? I thought I only need 1 additional vector for the basis, or do we need 2 additional vectors because we know we are in a linear subspace of R4?
So yeah, R4 is the interesting word here. So we have this R4. Oh, sorry. That's a 4-dimensional space. And we also have U. U is a 2-dimensional space. So that means U ortho also has to be 2-dimensional. You might remember that we have a formula like the dimension of U and the dimension of the orthogonal space. That adds up to the dimension of the original space. And in this case, that's R4. And once we know the dimension of U to be 2 and the dimension of the original space 4, that means the remaining dimension for U ortho must be 2. So that's why we need 2 basis vectors for that. So U and U ortho together span the whole space. So of course, their dimensions combined need to make up for the dimension of the whole space.
Can I also compute the kernel of U and then normalize to obtain U ortho?
What is the kernel of U?
Maybe, Jacob, you could maybe rephrase what you meant.
Please be careful with these expressions. So we defined the kernel for a matrix and by extension for a linear mapping. U is a vector space. It's not a matrix and it's not a linear mapping. So by definition, this does not have a kernel. You can try to define the linear mapping that is somehow related to U, and then maybe the kernel of that will help. And there is a method of doing that. Maybe that's what you mean, but I don't really see why that would be easier.
Okay, then there is a question that it says, couldn't we just add 2 vectors, U1 and U2, that are each 1, 1, 1, 1, and then apply Gram-Schmidt? Well, then we wouldn't have a basis, right?
Yeah, so if you have this B1 and B2, and then you add these 2 vectors here, and then apply Gram-Schmidt. That's what you want to do, right? Okay, so if you do that, then you can immediately see you don't have a basis, because obviously this is not linearly independent, right? Those 2 are multiples of each other. They're the same, actually. So you only have 3 independent vectors at most in there. There can't be a basis. So what would happen if you still apply Gram-Schmidt's method to that one? Well, if that is still linearly independent, then of course you'd get 1 more vector, 1 B3 out of that. So you'd end up with B1, B2. You would compute a new B3 from that one here. And then what would happen is that this vector 1, 1, 1 is of course included in the span of B1, B2, B3. Right? Because together, those B1, B2, B3 have all the components that you need to compose 1, 1, 1, 1. Because that's exactly what you did here. You composed that vector by its B1 part, its B2 part, and then you added the rest that you needed, the orthogonal rest, as B3. So with this here, you can compose this vector. And that means if you then apply Gram-Schmidt's method, what happens is the projection of this vector 1, 1, 1, 1 to span B1, B2, B3. Well, that means you can already compose a vector with those. And that means the projection would be exactly that vector. There is no orthogonal part anymore. Yeah, so you would decompose it into itself plus 0. And that means you would get B4 as 0. If you just did the computations, right? And before prime would be the 0 vector. And of course, a 0 vector is nothing that you want to add to a basis because it's not linearly independent. Also, you can't normalize it. It always has length 0. So you can't use that. And that means at that point, you would detect that something was wrong. So what happens is you can just do Gram-Schmidts. Everything will be fine until the third step. And then in the fourth step, you'll end up with this result. And at that point, at the very latest, you should be able to see that the input was somehow not a basis. But what you can, of course, then do is you can just ditch this vector here, add some other vector that you hopefully is linearly independent, and try again computing a meaningful V4. And that is exactly what I suggested in the very beginning here. If you remember that one. So say you wouldn't be sure that this actually is a basis. You could start with something like this, and then just apply Gram-Schmidt. And in case one of these vectors is not necessary, the Gram-Schmidt will just read the 0 vector. And if that happens, you just ditch that and continue with the next one. So in this case, you would be fine, right? After these 4 vectors, done, you have your 4 necessary basis vectors, no 0 vector so far, as we saw in these computations. And of course, you know the dimension that you need is 4, so you can stop after that. If you would continue, if you would then apply Gram-Schmidt to U3, in addition to the 4 you already have, the result would be a 0 vector. And of course, that could also happen in between. Say if U2 was linearly dependent on these 3, then what would happen is you would have B1, B2, you would get a B3, just fine. Then U2 would be contained in the span of those 3. So the result here would be the 0 vector. And what you do is you just forget about your B4 and your U2, and you continue with U3. Try again for a B4. And hopefully this time it would not be the 0 vector. If it is, again, just ditch it, continue with U4, and well, that's the last one you have. So you're bound to get a non-zero result then. So that's totally fine. If you know that you start with a basis, then you can avoid unnecessary computations. But if you don't know that, you don't have to make sure before. Just if something like this happens, you know that there were some linear dependencies and you just can't use that vector. So you just continue with the next one.
Okay, so are there cases where we cannot apply Gram-Schmidt with a given span?
I wouldn't know of any. Do you know some cases where you couldn't apply that?
I would say that if you have like a basis, like a properly given basis, it should be possible.
Yeah, so as long as you have a scalar product, of course,
yeah,
you should be fine. Yeah.
I never heard of any counterexample or any exception.
You may have a hard time if you have an infinite dimensional vector space.
Yeah.
But so in principle, the method would still work, but of course it wouldn't terminate.
Then there was a question. We could also select just in case of taking 1, 0, 0, 0 or 0, 1, 0, 0, like any of the 2 vectors, canonical vectors of R4. Yeah, that's possible. So you could take 0, 1, 0, 0 and 0, 0, 0, 1, 0. 0, 0, 1.
Yeah, I guess so, yeah. I haven't tried, but yeah, that should work as well. In this case, not necessarily in general.
Yeah, you always have to, I would say like you always have to be sure that the basis is a proper basis.
Yeah, correct. Yeah, so yeah, either you have to be sure that you have a proper basis or you just start with something that contains a proper basis for sure. And you'll run the risk of getting these zeros in between.
Why do we need B4? Isn't B3 enough?
No, because U ortho is 2-dimensional. So what we do is we determine an orthonormal base of R4, and that contains 4 vectors. So we need B4 as well.
Okay, what if the norm of B3 is a square root?
What then?
That is where I have had problems.
It doesn't really change anything. At least
Okay, I had one where the norm of B2 was the square root of 6 divided by 2. But it's still a number, right?
It's still a number, so you just take that. It might complicate your computations a little, but still it should work the same. And of course, just to mention that the result that we're getting here is by no means unique, right? So neither the B1, B2 basis is unique, nor the one that we have for R4. It depends on the order that you process your vectors in, and also depends, of course, on this extension here. So why did I do this? Here. So this choice here, adding U1, U2, that was completely arbitrary. You could have added any vectors that result in a basis here. And of course, the choice of vectors here influences your result. So you would get a different orthonormal basis for R4 if you choose different vectors, or if you just reverse the order. So your result might be very different from mine.
Why did we take 1/9 in B3?
In B3, simply because, let me scroll back here, because it was the least common denominator here. So here I have 2 over 6, that's 1 over 3. Denominator is 3. Here I have 2 over 18, that's 1 over 9. So the denominator here is 9. The least common multiple is 9. So that's why I took that, to have a 9th everywhere. And of course, if you don't have to do this, if you don't have to write that out, that's fine. Yeah, you can also do this in your head.
Could you leave out the coefficients of the vectors in the basis, as it is not states that U ortho has to be an orthonormal basis?
So if you want an orthonormal basis, then of course you'd have to keep those. If you just want an orthogonal basis, or any basis, then of course you would not have to keep those. You could just do without those then. Yeah, that's fine. But still, as I mentioned, at least for the B3, you cannot skip the normalization step, because you need a normalized B3 here in computing B4. You could leave it out at the end if you don't want an orthonormal base, but that's it. You still have to do the computation.
Okay, and now again there is this question: could we have also computed this with the vector 0, 0, 1, 0 and 0, 0, 0, 1? Well, in this case, yes. U1 and U2, they could still be linearly independent.
Yeah, so as I said, this choice here, adding U1, U2, that was completely arbitrary. You could add anything that results in a basis. So as long as you have 4 linearly independent vectors here, so add 2, that makes this here linearly independent, then you should be good, whatever vectors you choose.
And it might happen that the result is not the same, but it's still an
right. The result will probably not be the same, but it will hopefully still be correct. And you can simply check if that is a correct result by seeing if the vectors have scalar product 0, if they are orthogonal. They should be pairwise orthogonal, otherwise you messed up somewhere. But hopefully they will be, and then you have a correct result, even if it's not the one I got.
When we are doing the check before normalizing at the step where we found B3 prime, and before computing B3, do we have to check if B3 prime is orthogonal to both B1 and B2, or just to one of them?
No, you have to check whether it's orthogonal to both. So the new vector you compute needs to be orthogonal to all the old vectors. So when you compute B3, it needs to be orthogonal to both B1 and B2. When you compute B4, it must be orthogonal to B1, B2, and B3. And you should check all, of course, just to make sure that you got it right.
Why not just expand onto R3? Well, we have elements of R4, right?
Yeah, because we have elements of R4. So that whole problem setting is in R4, not in R3.
If we are talking about R5, how do we know which subspace has dimension 3 and dimension 2?
Depends on how they're given. So if we're talking about R5 and we have U as a space spanned by 2 linearly independent vectors, as in this case, then of course U will be 2-dimensional. It can't have more by definition. And then U ortho will be three-dimensional. If U is given as a span of 3 linearly independent vectors, then it's the other way around. And of course, I also have more options here. I could have a 1-dimensional U and a 4-dimensional U ortho, or the other way around, or maybe a 0-dimensional U and a 5-dimensional U ortho, or the other way around. That's all possible.
Yeah, so this is related to the next question. So if there would be 3 vectors in the basis of the U, O, and B, of U would contain 3 vectors, and the O and B of U ortho would only contain 1 vector. Yeah.
Yes, right. So if the O and B of U would contain 3 vectors, then that means U is 3-dimensional. So in this case, the dimensions need to sum up to 4. So U ortho must be 1-dimensional then, right?
Could we say that each basis describes a plane that is in R4 and each plane is orthogonal to each other?
Yes, you could say that. Yeah. So both U and U ortho are planes in the 4-dimensional space, and they are orthogonal to each other.
So a prerequisite for applying, I got lost. For applying Gram-Schmidt at linear independent vectors. Well, I would say basis, right? I mean, you need to have a basis.
Yeah, you need to have a basis.
Not just any linearly independent vector, but a basis.
I mean, you could start with a set of linearly independent vectors and then say, well, that's the basis of their span. So basically, that's the same thing. But if you have a space that you're talking about, then you want the basis of that space, of course. Mm-hmm. Depends on your starting point.
So the fact that the space of U is R4 does not have to explicitly state in the problem statement.
A space of U?
Well, I think, one has to be able to identify that the vectors, they have four components. So from there, you can already see that it's element of 4.
So V1 and V2 have 4 components each. So those are elements of R4. And that necessarily means U is a subspace of R4. And you should be able to get that from the problem statement. Yes.
How do I check that U is orthogonal to U? UT is orthogonal to U.
So in this case, you have a basis of each of those. You can just check whether the basis vectors are pairwise orthogonal. Right? If you have a basis of U and a basis of U ortho, then you just take the basis vectors of those 2 and check whether all possible pairs of one vector from U, one vector from U ortho, those are orthogonal. Any other vector needs to be it needs to be composed as a linear composition of the basis vectors. And that means the scalar product is also decomposed into a scalar product of pairwise basis vectors. And if those are all 0, then you're good. And they have to be, of course.
Now there is a question for the check. Does B4 have to be orthogonal to B1, B2, B3, or to B1, B2, U3? I'm a little lost what U3 is.
Why U3? So U3 would be the 3rd unit vector then, maybe? Which did not play any role here. So B4 has to be orthogonal to all the vectors that came before it in the O and B, and those were B1, B2, B3, generally speaking. U3, I don't really see what role U3 would play here.
I meant U2, like the vector we expanded with.
No, not U2. The vectors that you produced. So the vectors that make up your O and B so far. The new vector has to be orthogonal to those. So in this case, B1, B2, B3, not U2.
Okay, and there is one last question. Is there a more systematic way to choose potential vectors for U ortho? Because right now we're choosing arbitrary vectors and compute if they are orthogonal to U to determine U ortho.
So the most systematic way that I could think of would be to just take what you have, like here, B1, B2, and then add an arbitrary basis of the whole space. So you can be sure this whole set contains a basis of the whole space. And then just apply Gram-Schmidt, ditch all the 0 vectors that you get, and just keep the rest. So in a way, Gram-Schmidt will filter out all the unnecessary noise. You will just keep the vectors that are really necessary. And of course, that way you will have to do more work, but that's, if you want, that's a systematic approach without any guesswork.
Okay, 2 more questions that they just came. So as a result, B1 is orthogonal to B3 and B4, and B2 is orthogonal to B3 and B4.
Yeah.
Also the other way around, B3 is orthogonal to B1 and B2, and B4 is orthogonal to B1 and B2, right?
Yeah. Each pair of those vectors is orthogonal.
Just to make sure, when you have a B2 prime and you need to normalize it to B2 prime, is vector that is multiplied by a fraction 1/2, then you don't need to take the fraction into account when you calculate the norm, right?
Let me do this with B3 because I think that's, yeah. So here we have, for example, here we have a vector that is 1/9 times this vector here. So when you normalize that, you could either compute the norm of this, including the 1/9, or you could just compute the norm of this, excluding the 1/9, and then multiply with the respective vector. So you would either do like 1 over the norm of 1/9, 1 minus 2, 0, minus 2, times 1/9, 1 minus 2, 0, minus 2. Or what I did, I computed the norm of just this one here without the 1/9. And then, of course, you also have to multiply that by the vector without the 1/9. So basically, you forget about, or you scale that vector here with any factor you want before you apply normalization. The result is the same, because what happens here, if you just take this one here, this 1/9, that's a scalar factor, and you can take out scalar factors from the norm. So that would be the same as 1/9 times that norm. Oh, that's supposed to be a minus 2, by the way. Times 1/9 times 1 minus 2, 0, minus 2. Yeah. Like this. And then, of course, this 1/9 would just cancel out, and you're back at that point. Yeah, so it's usually easiest to just scale a vector to make it as easy as possible, and then apply normalization to that new vector. But if you'd rather do it the complicated way, of course, that's fine. That would get you the right result if you don't mess up. You're welcome to attend the tutorials and the Q&A sessions and ask your questions there. Otherwise, I'll hopefully see you next Monday. So thanks for attending, and thanks to Lissery for moderating.
My pleasure.